presentation.
Okay, so my thesis topic, I would like to work on an ECF-driven Gecko robot using electro-adhesion. So analyzing this title, ECF-driven refers to the method of actuation for a soft robot. ECF stands for electro-conjugate fluid, which is a type of dielectric fluid which generates a flow under high DC voltage. This is the core mechanism that is used to actuate the bending actuators of a soft robot. Why a Gecko robot? We will see later, analyzing the advantages and disadvantages of this method of actuation. So a bit of context. A Gecko model is a Gecko robot is modeled through inspiration from nature, but the actual natural body of a gecko is over-actuated and needs to be simplified to be small enough and lightweight enough to work. This is an example of a simple gate of the robot. The green circles represent pads that are attached to a wall or a surface, while the red pads show pads that are not attached to a surface. So by moving the two diagonally opposed legs forward and then attaching them to the wall and then repeating the process for the other diagonal, the robot is able to move forward. By switching the combination of what legs are moved forward and what pads are attached, we can also make the robot turn to make the robot have freedom of movement in every direction. Why Gecko robot is useful in the real world? A climbing robot, especially if it is small, can be very useful to explore specific environments that may present small slits or tunnels that are very difficult to explore using a flying vehicle, but may need climbing or ceiling walking to be explored. So let's analyze the state of the art. Right now I chose to look carefully at two main robots. The first one is from a paper from 2015, which shows not a soft robot, but a robot that uses electro-adhesive pads to attach to the wall, which is also the way I want to make my robot stick to a surface. And we will see later why. The second robot I looked at is from a paper from 2019, which instead uses vacuum adhesion and a soft robot body. These are soft actuators that can bend, and in this slide we can see how the robot may move itself forward by bending its body and its leg at the same time to, as we talked before in the gate process, move forward the two opposite, diagonally opposed legs and proceed forward. These robots have some aspects that can still be improved. And the main aspect I want to focus on is the fact that the body of the robots, both in this one and the previous one, are not able to bend and make the robot have a transition between a wall and a floor, or between a wall and the ceiling. So, talking more in depth on my idea for the robot is to use the electro-conjugate fluid actuation method that is developed in the Takemura lab in KU University. This method focuses on creating the flow of the dielectric fluid by having very small pair of electrode, in particular a ring electrode and a needle electrode, which are separated by several hundred micrometers. And under high voltage, and this high voltage ranges from 4 to 6 kilovolts, the ECF shows a strong flow, which is used to actuate this type of actuator. This was initially developed as a robotic finger for a hand, and the main mechanism is the fact that there are 4 different ECF jets, 2 main chambers, and 2 connectors. When the DC voltage is applied, these 2 jets propel the fluid on the right chamber, while these other 2 jets propel the fluid towards the center of the chamber, making possible a difference in how much fluid is present in the left chamber compared to the right chamber. And this is the mechanism that lets the bending actuator actually bend. What are the advantages and disadvantages of this method of actuation? We need to compare it with other soft actuation methods, which, for example, a pneumatic, which is the most common actuation method, shows a problem in how it needs the pressure from an external source, while this type of actuator presents inside of itself the whole fluid, the pressure generator, the ECF jet, with a pair of electrodes, and also is small and lightweight. This robotic finger is about 30 millimeters long, which makes a good use in a Gecko Robot that can be very small and lightweight. What is the main disadvantage of this method of actuation is the fact that it requires 5 kilovolts. This problem is especially shown in the power supply, but how else can we use these 5 kilovolts? My main idea was to use electro-adhesive pads to stick the robot to a surface. Electro-adhesion is a method that uses high DC voltage, again around 2 to 5 kilovolts, and based on how strong the electric field is applied to the pad, the higher the adhesive force is. In Kakinuma lab in Keio University, they developed electro-adhesive pad based on electro-rheological gel, and their improvement on it was an electric field assisted molding process, which makes it able to have more electro-rheological particles on the surface and improve the performance. Lastly, I want to talk about the power supply. Obviously, the power supply needs to be tailored specifically for this type of project. It needs to provide very high voltage, but very, very low current, because the other main advantage of ECF actuation is that it requires current of around 30 microamperes, which in total makes the whole actuator be very, very low power needed. So my state-of-the-art improvements are a smaller size and lightweight, and a robot that can transition, as it shows in this image, from a wall to a floor, and other combinations of floor, wall, and ceiling. And lastly, this is a way to go towards an untethered mobile soft robot, meaning a soft robot that doesn't need a cable or a tube for air pressure connected to it. Lastly, the bibliography where I found information.
Okay, thank you. So, how many degrees of freedom will you have if you suppose that when you bend, you have 1 degree of freedom per actuator?
Yes.
Because
so the structure, the main model of the robot is what I want to work in the next semester. My supervisor from ECN will be Stefan Caro, which is
yes.
which agreed on working on the design of the robot
Okay.
to have as less actuators as possible, but still maintain the goals of the project.
Yeah.
Yes.
So you will have how many actuators? You think you will have 1 for each leg and 1 for the body?
Probably yes. For the body, I was also looking at omnidirectional bending actuators, which can be manufactured by combining 3 different bending actuators. And there's a student in Keio lab that is in Takemura lab, which is currently working on an omnidirectional bending actuator using ECF.
Okay. And so for the high voltage, will it fit on the high voltage regulator? Will it fit on the robot itself? Because if it's very small.
So for sure, it needs to have specifically manufactured power supply.
Okay.
Yeah, as it was shown in this slide. So the power supply is the size of the power supply depends on how much power it needs to output. But since the voltage is very, very high, but the current is very, very low, around 30 microamperes, the overall size of the power supply should be very small, because of a very low power needed. And this is an example of a power supply that was used for micro air vehicles, which also used electro-adhesion, which is another method, another mechanism that requires very, very low current because it is an electrostatic mechanism. So only current leakage is what uses power, basically.
Okay. Okay, thank you.